Okay, welcome everyone. Welcome to the very first NDC Minnesota. It's the first session after the keynote, so hopefully everyone's awake and raring to go. So my name's Stephen Haunts, and we're talking today about protecting encryption keys using Azure Key Vault. So it's not just about the default use of Key Vault in Azure, it's about how we can actually program against the Key Vault. So I'm a freelance developer and independent trainer, so I run a business called Stephen Haunts Training. I've also been writing courses for Pluralsight for the last 4 years. So I've now got 13 courses in the library and I've got another one on the way soon. So if you're a Pluralsight subscriber, please do watch my courses. And I'm also a consultant with a company called Block3. So we go into companies and we help them identify whether they actually want a blockchain in their business or whether they actually understand what it is they're talking about when it comes to blockchains. So we help them work through that problem. A couple of courses that I've got that might be of use to you if this is a subject you're interested in. So the first one is called Enterprise Data Encryption with Azure Reveal. So it kind of covers some of the stuff that we're going to talk about today, but we go in a lot more detail today. And I've also got a course called Practical Cryptography in .NET, which goes into quite a lot of depth about a lot of the crypto APIs in the .NET framework and .NET Core. So a rough agenda of what we're going to look at today. So we're going to talk a little bit about data breaches and the effects on companies. We're going to do a very quick cryptography overview, just to make sure everyone's on the same page. Then we're going to explore some of the different key management options that are out there, good and bad. Then we're going to introduce the Azure Key Vault, and then I'm going to talk through various different patterns and practices that you can use with the Key Vault and Visual Studio. So the threat of data breaches. So I always like to bring this slide up when I do talks about security, and this is a website called breachlevelindex.com. And I like to show it because it really puts the numbers up there, sort of in the forefront. So we can see at the top here that since 2013 there's been 9.7 billion records lost or stolen by companies. And the scary thing is that number doesn't actually really surprise me anymore. It's a problem that's constantly getting worse. The bit that is worrying is the line underneath where it says only 4% of breaches were classed as secure breaches. And by secure they mean, was the data encrypted that was being stolen? And only 4% of cases was that data actually useless to the people that stole it. So a few more stats underneath. So about 5 million records every day are stolen, which is about 200,000 every hour, which is 3,500 every minute, or 58 records every second. That just really kind of sort of highlights what the problem is, or how big the problem is. And we've got some examples here from the same website. So lots of sort of household names on there, especially in the US. So JP Morgan Chase had 83 million records stolen, which was identity theft. Equifax, nearly 150 million records stolen. MySpace, I'm surprised they've still got 360 million customers, but there you go. I'm obviously too old for websites like that. And then if you look at websites like Troy Hunt's Have I Been Pwned, has anyone signed up to this service that Troy has? It's very good. So if you sign up to it, whenever your email address appears in a data breach, you get notified, so you know to change your password on that site or close your account. And there's some good stats on here as well. So Adobe, 152 million records. LinkedIn, 164 million. There's a few dodgy websites on there. We won't go through those, but it can happen to any website. So what are the effects of data breaches? So for a company, the organisations that you work for, a data breach can be quite catastrophic. So it can cause a lot of reputational damage because people just won't trust you anymore. That can in turn lead to a loss of sales, so it directly affects your bottom line and your revenues. It could also mean that customers, again, won't trust you, so they'll switch to a competitor. And once they've switched, they're probably not likely to come back. You can also get lots of legal action from your customers and other companies. So class action lawsuits against you can be very costly. And also there's compliance costs. So if it's a PCI DSS breach where you've lost card data, that can be quite catastrophic for your company. Or other things like HIPAA, health insurance, personal information and health records have been stolen. And it could also compromise the safety of your customers depending on what your business is. So the consequences for your company can be quite bad. And then we can also look at the consequences for the individual. So you've had your personal data lost, your name, address, phone number, email address. That means your address where you live could be out there on the internet for anyone to look at. That can result in ID theft and impersonation, which can then mean that you lose financial data, or people use your financial data that's been stolen to make purchases against your account. And it could also mean that you've had your transaction history stolen, so if you've bought anything that you might be a bit embarrassing, then that data could be stolen and people could know about it. So it's going to be quite a bad effect for the individual as well. But the scary thing is, data breaches these days are inevitable. They're going to happen to everyone or anyone at any point. It doesn't matter whether you're a large multinational conglomerate or whether you're a small to mid enterprise or even a small startup. It can literally happen to anyone. So what you need to do is change your mindset. It's not a case of if you're going to get data breached. You need to have the mindset of when you get data breached. And that kind of changes your whole perception of how you're going to deal with the problem. A lot of companies just tend to focus on their perimeter security. So that's things like firewalls and intrusion detection systems. And these are absolutely good things to do. You shouldn't stop doing that. But it's not the only thing you should focus on. So what we want to talk about is encryption. So that's encryption of data at rest and also in transit. Now you need to spend a lot of time identifying what it is you want to encrypt. So generally that's going to be things like personal identifiable information, anything that can relate back to a person, either living or dead. Credit card data, payment card information, PCI DSS, regulated data, or just anything that's sensitive to your business that you don't want people to read. I put the GDPR slide in here because even though we're in the US, GDPR, whilst it's European regulation, does very much affect pretty much anyone on the planet because we live in a digital internet economy these days. So if your company has any European customers, whether it be individuals or companies, then GDPR is very important. And this includes things like how you protect people's data using encryption. If they want their data updated or deleted, then that's their right to do so. So you have to be able to build all these processes into your systems. And the penalties for GDPR can be quite significant, so they're designed to hurt if you get caught or get caught up by the regulation. Okay, so let's do a very quick high-level cryptography overview of just some of the things that we're going to be playing around with in a bit. So cryptography can basically be split down into 4 core areas, or 4 pillars. So we have confidentiality. This is what everyone typically thinks of with encryption. You have some data, you encrypt it, make it secret, then you can decrypt it. Integrity. This is what we commonly solve with hashing. So you have some data, you create a hash code of it, send that data across the network, recalculate the hash code for that data. If they match, you know that the data's come across intact. If the hash codes don't match, you know that there's a problem with the integrity of the data. Authentication is kind of an extension to hashing, but it allows you to do hashing with an encryption key. And what that means is that for someone else on the receiving end of that data, for them to calculate the same hash, they have to be in receipt of the same encryption key. If you haven't got the key, then you can't recalculate the hash. That's why we call it authentication, because it's a bit like a password. Then we've got non-repudiation, and this covers things like digital signatures. And what that's effectively like, it's kind of more like a contract. So if you create a digital signature of something, then you can then prove that that signature was created at the appropriate time. So it means, kind of like with a contract, if you sign a contract, you can't then go and deny it later on. That's kind of what a digital signature gives you. So in .NET, we typically use things like AES and RSA for encryption. And we've got lots of different hashing algorithms we can use, but very commonly we'll use SHA-256. Authentication, we use something called a hash message authentication code, which is effectively like a SHA-256 hash but with a key. And then we can use digital signatures. Then if we use all of those things together to create different protocols, that's called hybrid encryption. And we're going to look at some examples of that a little bit later. Okay, so encryption. Generally we have 2 types, symmetric encryption and asymmetric encryption. So symmetric encryption is where you use the same key to encrypt and decrypt your data. And typically we'll use AES, DES or triple DES. The reason I could include DES and triple DES on there is you wouldn't really want to use it for a new system, but if you're integrating with an older legacy system, then being able to decrypt DES data might be very important to you. Then on the other side of that we have asymmetric encryption, so things like RSA. And the difference there is the key is split into 2. They're mathematically linked keys, but you generally, you encrypt with the public key and you decrypt with the private key. So if I want to send some data to one of you, I'll use your public key to encrypt the data, then you decrypt it using only your private key, which only you know. Now with symmetric encryption, it's generally very fast. It's very algorithmic. That's what computers are good at. It takes data, splits it down into blocks, and does lots of algorithmic operations to it. So it's very fast, but a symmetric key is very hard to share. So if I've got a key and I encrypt some data, how do I give it to one of you? Do I send it to you across a network in the clear? That's not a good idea because it could be intercepted. Certainly don't want to email it to you. So really the only way of getting the key to you is if I sort of physically hand it to you in person. On the flip side of that, we've got things like RSA, which generally is quite a slow operation because it's very mathematical. It all uses prime numbers and modulus arithmetic to perform its operation. So it's not very fast. But what it does give us is a better way of doing key sharing, because the private key you keep to yourself, that's only yours. The public key you can give to anyone. So it actually makes the way of sharing keys for that a lot easier. Now in .NET, there's two classes we'll use for this. We'll use AES Crypto Service Provider for AES, and for RSA, we use RSA Crypto Service Provider. So those are the sort of the very high level overview of some of the crypto primitives available to us. So what about key management options? So we said that generally keys can be quite difficult to share. So one way you can do it, and I don't recommend doing this, but I've worked at several companies that have done this, and I sort of changed it when I got there, but storing keys in XML files on a server, really bad, don't do it. As I say, I've worked for two very large companies that did do that. But if it's on a file or a folder in a server, someone can easily access it and take the keys, so don't do that. But the one we're all very familiar with is certificates. You've got things like Kerberos certificates and X509 certificates. Very robust, been used for a long time, everyone understands them. So that's kind of a really good way of sharing keys and installing keys on different systems. And they'll store things like the identity of who you're issuing the certificate to and who it's been issued from. It lets you do public key verification. You can easily install it on servers. And it's a robust and proven mechanism, as I said, generally it's very well understood. And some of the benefits is, for the end user, there's minimal involvement. If you're installing a big enterprise system, generally the certificates will be automatically installed by the system, so the end user doesn't really have to deal with it. You don't need any additional hardware. Most modern operating systems like Windows, etc., have a key store built into the system. Easy to manage. IT systems, IT departments all over the world are used to dealing with certificates. And they're supported by just about everything. But there's an extra level we can go to. And that's to use something called a hardware security module. So what this is it's a 1 or 2U rack mount appliance that you put into your data center. Got some examples here, but there's a few issues with it. Well, actually, let's go over what they do first. So first of all, they're tamper-proof. So if anyone tries to hack into it, it will detect that and wipe itself and clear all the keys off the system. If someone tries to physically break into the system, try and take the cover off, it will have lots of tamper mechanisms on there, so it will detect when the screws have been undone and it will wipe itself. It can have light sensors, temperature sensors. All of the chips are covered in an epoxy resin onto the board. So it's very difficult to actually read anything from the chips inside it. You can use them for storing keys and also certificates. But the problem is, traditionally, hardware security modules have been cost prohibitive for a lot of companies. And I've worked with some sort of large banks in the UK, and we did have HSMs in place. And also worked for a retail finance company where we got some HSMs in. We had to buy 2 of them because ideally you want 1 different data centers with the key synchronized between the 2. We paid probably about £75,000, which is, what's that in dollars? $120,000 maybe, thereabouts. So they've been very expensive. So for smaller companies, it's kind of something that you can't really entertain because it's just too expensive. This is where we have wonderful things like Azure, which allows us to do lots of great things in a cost-effective way. So they provide something called the Azure Key Vault. So Azure Key Vault is a wrapper around physical hardware that's stored in their data centers, and they've made it very easy to program against. And the hardware they build it upon is this device here, so it's called the Thales N-Shield. So I don't know how many they have, but it's probably lots per data center in each of the regions around the world. So they provide an abstraction over this system, which you can use. So Microsoft has taken the hit on the cost of buying these devices, and we can use them for very little money. And some of the techniques I'm going to show you later, you'll be able to get your cost down to virtually nothing. Now, Azure Key Vault has 2 concepts. You can use hardware and software to store keys and do encryption operations. And there's different pricing tiers, which we'll look at. But effectively, whether you use the hardware or the software version, all of your keys are ultimately stored inside the HSM in hardware. But if you use a software system, which is slightly cheaper, then the encryption and decryption operations are performed on compute VMs in Azure, but using the keys inside the hardware. So because they're reducing the amount of time they're using the HSM, the costs come down a lot more. But you can also use the full hardware version, which means all the encryption and decryption operations actually happen on the hardware itself. You pay a little bit more for that privilege, but this is that's kind of the more robust version of using it. So generally, the recommendation is if you're using test and dev environments, you might just use the software version. The results are the same, what you get back and put in. But in your production system, you'll want to go for the full hardware version because that will give you the most protection. So if we have a quick look at some of the costs, so there's 2 pricing tiers, standard and premium, that you can use with Key Vault. And if you're storing things like secrets, and we'll talk a bit more about secrets later, but if you're doing secret operations, then it costs about 3 cents per 10,000 operations across both pricing tiers. If you're doing certificates or storing certificates, and it costs $4 per renewal and then 3 cents per 10,000 operations. So already the costs are quite low. So if you're using software encryption operations, so if you're using the default, which is RSA 2048-bit keys, then again, across both pricing tiers, it costs about 3 cents per 10,000 operations. And those prices are accurate to about last week. They are introducing higher strength encryption keys, so 3072 and 4096-bit keys. Currently they're free because it's in like a preview period. I don't know what the final cost of that will be. But you have the option to use the higher strength keys. Now if you're using the hardware HSM key operations, then the costs are a little bit higher, which is why I recommend you might just want to use that for production and the software ones for your test environments. So these are only premium tier, so RSA 2048-bit keys, you're looking at about $1 per key and then 3 cents per 10,000 operations. And then the higher strength keys, it's kind of a tiered pricing model, so your first 250 keys will cost you $5 per key, and then that sort of scales downwards. And then it's about 15 cents per 10,000 operations, so a bit more cost. Now, a key thing to remember with something like Azure Key Vault is once you generate a key and it goes in the Key Vault, it will never come out again, so you can never see the key. You can actually do a backup of your keys, but all those keys are encrypted by a master key on the Key Vault, so even though you might back them up in your company, you can't actually access the keys inside them. Okay, so setting up the Key Vault. I'm not going to run through the process of setting it up, so you haven't got time this morning, but the Microsoft documentation is actually really good. So if you just type Azure Key Vault setup or something like that into Google, you'll find it, or there's a URL down there, and that will take you through the process of setting it up. But generally what you're going to do, you set it up using PowerShell, you create a resource group, or you might use an existing resource group. You create the Key Vault specifying the resource group, the region, and whether you want hardware or software variant. And once you've done that, you've got the ability to create keys, read and write secrets, and upload certificates. And once that's done, you can just access it as a standard blade in the user interface. Now, if you want to do programmatic access against the Key Vault, which is something we're going to look at in a moment, then you need to do an extra step. So you need to register your application with AzureAD. All the instructions for doing that are in that website. And that gives you your app ID and shared secrets that you need to use to access the Key Vault. So we talked a bit about secrets, so there's a difference between the two. So keys are RSA encryption keys, so your public and private key, which gets stored in the Key Vault. What a secret is effectively it's up to 25k of text that you can store in the Key Vault. Now you don't control what keys you generally use, well, actually you can specify the key, but what it's doing is it's encrypting text files or data inside the Key Vault, which you can retrieve later. So a good excuse, well, a good reason for using this is things like connection strings or API keys to third-party systems. Instead of putting them in config files, which you might traditionally do, you can store them as secrets in the Key Vault. So I've got some sample code which we're going to sort of look through today. It's all on GitHub. I've released it under an MIT license, so feel free to steal it and do what you want with it. Each sample application is a console app that runs completely independently from the other apps, so you can get them up and running really easily. So we're going to go through some of those today and hope the Wi-Fi gods are favourable to us. So when you set up a project, you have to include a NuGet package, so it's a Microsoft Azure.Key Vault package. It's .NET Core, .NET Standard compliant, so I mean, I'm doing it on a Mac, but it doesn't really matter if you're doing it on a Mac or on Windows, and all of this code will work on normal .NET Framework as well. You just need to change the project file type. So let's go and have a look at a small example. So in the solution, I've got loads. Oh, I need to catch up. So in the solution I've got various little projects that you can play around with, which are going to cover some of the patterns we're looking at later. But the first one though, we're just going to do a simple encrypt and decrypt operation on the key vault. So let's run this and we'll step through it. So in the code I've created, I've got a class here called Key Vault. I've got some example client ID and secrets in there. The Key Vault that uses this is going to get destroyed after the conference. So don't think you can just go and use this one. But I've got a wrap around some of the stuff that's in the client library from Microsoft, so I'm only exposing the actual bits that we need. So what we're going to do is we're going to step through this. I'm going to create the Key Vault. So now we've instantiated the Key Vault, so it's opened the connection to the Key Vault. Now what I want to do is I want to create a key inside the vault. So I've called it Stephen Hawkes' key. I'm going to step over. Come on, Wi-Fi, you can do it. So that's created a key on the Key Vault now. So that's stored off in a data center somewhere. Partly the reason why it's running a bit slow is I'm using one of the UK data centers, so it's going back over the Atlantic. But we get a key ID back, so that's a URI to the key in the Key Vault. And that's what we're going to use to specify in our encryption operations. So I've got a text string here, Mary had a little lamb, I want to encrypt that message. So what I'm going to do is I'm going to convert it into a byte array using the get bytes method there, and then I'm also going to specify the key ID. So I've done that. I've now got a byte array which is my data encrypted. Now I can decrypt it. Now if I convert both of those byte arrays back into strings, then we can view them. So that's our encrypted text as a base 64 encoded string. And then see where we've decrypted it, it's gone back to Mary had a little lamb. So that's doing an encrypt and decrypt operation using RSA on the HSM. So that's kind of that's hello world in Azure Key Vault terms. Okay. Right, so that was our hello world, so we know the Key Vault's working. Looks like the Wi-Fi is going to be kind to us today as well, which is good. So there's various different patterns and practices around using the Key Vault. These are all things that I've sort of picked up and worked with over the last sort of 2 or 3 years of using Key Vault. So we're going to talk about multiple environments, configuration of secrets, local key wrapping, key versioning, some little tricks we can do with password protection, and digital signatures. So those are the things we're going to look at. So first of all, I just want to talk about multiple environments. So typically when we build our systems, we have production environments, UAT environments, dev, test, and whatever environments you need to get your systems from development into production. First thing you want to make sure you don't do is just use one shared key vault across all of your environments. You need to treat your production system and your production keys as completely secret, so no developer should ever have access to them. Now you might do something like this. You might have a shared key vault you use for your test environment and then a separate one for production. I've done that at one company and that worked quite well for us. The one we used for the test systems was using software operations on the Key Vault, and then the one we had in production was the full hardware, sort of the higher cost version. Or you could go a bit further. If you script all your environments, you could just have a separate Key Vault per environment. Both of those are fine, but just don't share the same vaults for production across all your test systems. That's a big security risk. So configuration as secrets. So as we said, you can store secrets on the Key Vault. So they are a maximum of 25k blobs of text. And these are stored in software, but they're encrypted using a master key on the HSM. So typical things you might want to store as secrets are connection strings, API keys to third-party systems, Redis cache connection strings, something I've used before, and just anything that you don't really want it to expose to anyone. The sort of things you sometimes panic and go through GitHub trying to delete. Those sorts of secrets from config files. Secrets are versioned as well, so if you have a connection string and you call that secret my connection string, if you write it again twice, it will create a second version of it in the Key Vault, so you can actually do version control across settings if you want to. So let's have a little look at that. Code for this is incredibly straightforward. Everything to do with Key Vault and using Key Vault is actually quite straightforward. If you download the source code, it's all written for you, so just take it and use it if you want to. So again, we're going to instantiate the Key Vault. I'm going to create a secret called Stephen Haunce's secret. And again, my secret's called Mary Had a Little Lamb. So I literally just send that to the Key Vault. Now that secret, Mary Had a Little Lamb, is sitting inside a HSM in an Azure data center. Then to retrieve it, you just retrieve it by name. So that's pulled it back off the HSM. And then we can see the text in our string there. So incredibly easy to use. It literally is just a key value store, but it's on protected hardware. So it's a great way and a very simple way of protecting data. And this next one here is local key wrapping. This is where we can actually start to get the costs for Azure Key Vault drastically reduced. So encrypting on a HSM is generally expensive, and I don't necessarily mean cost, I mean in terms of network hops. I mean, I'm accessing a Key Vault that's in the UK at the minute, and you could see there was a bit of latency in doing that. So if you've got to encrypt, hundreds or thousands of pieces of data in your API calls or your websites, that's going to really affect performance. So what we want to do is we want to use a technique called local key wrapping. So what this means is that all our encryption operations we'll do locally using AES. We talked about AES earlier, it's a symmetric encryption system. But what we do is the keys that we generate for AES, we then go and encrypt using an RSA key on the HSM. And once we've encrypted that AES key, we can just store it in the database along with our data. If that data gets compromised and they get access to that AES key, it doesn't matter because it's encrypted, it's just garbage, unless they can access a data center at Microsoft and decrypt it. Let's have a quick look at that. So in this project here, I've got some extra classes. I've got one called AES Encryption, and that just does basic AES encryption. Again, you can just steal that method with these methods. So the way AES works, you give it a byte array for data you want to encrypt, you give it a key, so that's going to be a 32-byte random number, which we're going to generate. Then you give it something called an initialization vector, and that's just a 16-byte random number, which you then need to store with your data. That just helps jumpstart AES. So we've got an encrypt operation, and we've got a decrypt operation. So there's nothing Azure Key Vault specific there, that's just standard AES encryption in .NET. Also got a method here, or class here called random, and this is what I'm going to use to generate my local key. So it uses a class called RNG Crypto Service Provider. Really nice naming by Microsoft, but what we do is we pass in a length, so 32 in our case, of 32 bytes, or 256-bit key. Instantiate the RNG Crypto Service Provider, we call getBytes, and then that returns us our 32-byte random number. So that's how we're going to generate our local key. So let's look at that in use. Right, so instantiate our Key Vault. I'm going to create a new key on the Key Vault. Each of these sample apps creates and deletes the keys at the end, so it tidies up after itself. Right, so now what I'm going to do is I'm going to generate an encryption key to use with AES. So I call my random number generator, and that gives me a 32-byte array, which is our local encryption key. So now what I want to do is I want to protect that encryption key with the Key Vault. So I call the encrypt method, I give it the key ID of the key on the Key Vault, and I pass in our local key. So now we have a completely encrypted encryption key. So you can convert that to a base 64 string, store it in your database, and go off and do something else. So then when you come back and you want to do an encryption and decryption operation, before you can do that, you need to recover that encryption key. You can't use it as is because it's encrypted by the Key Vault. So what we're going to do is we're going to decrypt it. So we pass in the encrypted key and the key ID of our vault key. And that gives us back our key in there. I think they're going to show me. Yep, so we've got our 32-byte key recovered. So now I'm going to generate my initialization vector. Now literally is just a 16-byte value. You need to store that with your encrypted data, but it doesn't need to be kept secret. So now I'm going to do a local encryption operation. So I've got a string here that I want to encrypt, mega top secret stuff. So I convert that to a byte array and then I encrypt it. So that's done locally, so there's no key vault operations there, I'm just encrypting locally in my process. Then I can decrypt it straight away if I want to. So if I convert both of those to strings, you can see the encrypted data there. So the string mega top secret stuff is encrypted. And then when I decrypt it, you can see I've recovered it. So what we've done there is quite powerful. So we've managed to use local key operations, so we're not constantly hopping over to the HSM. But the key we're using for that local key operation, we're protecting with the HSM. So if you've got a really big high-scale system and you're doing lots of encrypt and decrypt operations, instead of being charged 3 cents per 10,000 operations, all we've done is a couple of operations there. We've created a key, we've encrypted and we've decrypted our master key, so 3 operations. But then you might have 10,000 local operations, local encryption operations, but you're not being charged for that because you're just doing that locally. So it's a good way of bringing your costs down to virtually nothing. Okay. So an example where I've used this, the last time I used it, I was working for a company that does insurance claims management. So we was building a software as a service solution. So it was our solution, but then we could onboard insurance companies onto that system. So we use this in a few ways. So every time we onboard a new company or a new tenant, they get a completely rebranded version of the system to their branding. So it's a multi-tenant system. And what we did, we made sure that each of the insurance companies that came on had their own sets of master keys. So those master keys were RSA keys that were stored on the Key Vault. Then what we'd do is the data that we're dealing with those insurance companies, we'd encrypt and decrypt it locally within our system. So we were encrypting things like the claimant's information, so names, address, phone numbers, email addresses of the person making the claim. And then some of the claim details, so the vehicle details, was also encrypted. So if anyone ever came in and stole any of our data from Cosmos DB or SQL Server, all that data is encrypted. But the good thing is, because each insurer had its own set of master keys, effectively what you're getting is partitioning via encryption. So everyone's data was stored together in one big database. But the data was effectively partitioned because we was using different keys per insurer to encrypt their data. So effectively what that looked like at a very high level. So we had, we've got our system on the left there at the top. We had a whole bunch of app services and web services and all that stuff. We had SQL Server databases and Cosmos databases. Then each insurer gets their own key in the key vaults. So locally in our database, we're storing something like at the bottom. So we've got a tenant ID, that's the ID for our insurance companies. We've got the key ID, which is that URI that you saw when we created the key. And then we have a bunch of encrypted AES session keys, which are the local keys that we use for that insurance company. So the advantages then, so this means doing encryption, local encryption, is a lot faster because you're not constantly hopping over to the key vault. You're just using it to create and recover a key. So as you go into a web API method, we'd request the key for that insurance company, decrypt their local key, and then we could do a whole bunch of encryption and decryption operations in one go. And this also makes it easy to rotate keys as well. So a lot of companies, you might have a security officer, and one of the rules they might put in place is that you have to change master encryption keys every 30 days, for example. Now, if you're not doing local key wrapping and you're encrypting all of your data in your database using just that master key on the HSM, when you change that key in Key Vault, you've then got to go and re-encrypt all of your data. So that's incredibly inefficient and not really practical. But with the local key wrapping variants, when you change the key in the Key Vault, all you have to do is decrypt and then re-encrypt that local key. You don't need to touch any of your other data. Because the AES key you're using to encrypt that data is the same. You're just protecting it with a different key in Key Vault. So again, that makes it very easy for you to be able to routinely change your keys. You can even automate it. You could just say every X amount of days, change the key on the Key Vault and then just re-encrypt that local key. So we get some definite benefits there. Okay, so next one is key versioning. So changing keys over time is important. It's kind of like the digital equivalent of changing your locks when you've been broken into. Although you wouldn't necessarily just wait until you've had a data breach to change your keys. As we said, you might do it routinely. There's a couple of ways or a couple of techniques we can use around here. So this is what we just looked at. So you've got a key in the Key Vault, which might be version 1, and you use that to encrypt your AES key. You might remove that key and create a new one, which is key 1.1, which means you just need to re-encrypt that one local key. The rest of your data doesn't need to be touched. But another thing you can do is something called incremental keys, and I'll give you an example of where I've used this in a minute. So what this means is you might have key version 1 and you encrypt a whole bunch of data with that key. Then you create a new key, which is key 1.1. Instead of touching any of that existing data, you just start using that key going forward. So you have some data encrypted with key version 1, and then the rest of the data encrypted with key version 2. And as you increase, or you create key version 1.3, you carry on encrypting from that point. An example of where I've used this is a retail finance company I was working at was going through PCI compliance, and we decided to build our own PCI card token vault. So this is effectively a secure database on a separate network where we store everyone's card details, credit card numbers. So the policy we had on that, and was working with a PCI auditor to help build this, is that we had a policy where, say, every 250 cards that get stored in the key vault, in the card vault, we would change the key every 256 cards, every 200 or so cards that comes in. So that's an example where you can use incremental keys. So password protection, this is where you can do some other little tricks using the key vault when it comes to storing passwords in your system. I mean, we all know passwords aren't great. As technologists, we hate them because they're very insecure. But they're here to stay, and they're not really going to change because it's easy for our end users. So let's go through a little potted history of how to deal with passwords. So I think everyone can agree that plain text passwords are bad. Unfortunately, there's still a lot of sites out there that do it. Has anyone seen the Plain Text Defenders website? Where companies who use plain text passwords get outed to the rest of the internet. It's worth Googling, it's quite funny. But plain text passwords, we can all agree that's bad. So the next thing people do is use hash passwords, where someone types in their password, my password, then you create a hash of it, SHA-256 hash or an MD5 hash, and you store it in the database. Does anyone work on systems that does it that way? A few. So that's been one of the common ways of doing it. Unfortunately, there's a problem with that, in that it's very easy to brute force those passwords to recover them, or to do what's called a dictionary or rainbow table attack. So when you use tools like Hashcat, which is a freely downloadable piece of open source software, that uses your hardware's GPU to try and brute force passwords using massive multi-gigabyte dictionary files. So if you're just doing hashing with passwords, chances are it's going to be very easy to recover that password. I teach a workshop on this. Last time I did it, I had sort of 15 people in a room and was all running Hashcat at the same time, trying to break a load of passwords. And it kind of warmed the room up quite a bit as we was all running it. But everyone managed to recover all the passwords that we were looking for. So hashing, it's better than plain text passwords, but it's not perfect. Good example of a site here called crackstation.net. This is always good to show in demos, especially if you're trying to prove security principles to people in your office. So you go to that website, you put in your hash password at the top, type in a quick captcha, hit crack passwords. It's worked out that it's a SHA-256 hash and the password of secret 69. And you can also go and download the password table that they're using as well for that website. So hash password's better, but still not great. So a better solution then is to do salted hash passwords. And what this is it's kind of the same as what we just looked at with hash passwords, but you add what's called a salt onto the end of the password. So typically when I've done this, I've just generated a 32-byte random number, and then just appended it onto the end of the password, and then hashed it. Then you store the hash password and that salt in your database. And that makes it much harder for tools like Hashcat to be able to crack the passwords. But as GPUs get more powerful, what are they going to be like in the next 5 to 10 years? A password that's salted and hashed now that might be secure might be compromised in a few years' time because of the advent of GPU processing power, which is commonly used to crack these passwords. So what we want to do is we want to try and beat Moore's law. We don't want the advent of faster machines making it easier to crack passwords. The next popular one is to use something called a password-based key derivation function, or bcrypt. Does anyone use anything like that at the moment? Right, okay, so the mechanism built into .NET is called a password-based key derivation function. There's another one called bcrypt, which isn't supported in .NET, but you can get open source implementations of it. And the way this works is you have a password, and you have a salt, just like what we talked about before. Then you pass in a number of iterations. And what this does is it repeatedly hashes the password, and then you get a final hash out at the end. So what this is doing is it's algorithmically slowing down the password hashing process. So if you imagine a tool like Hashcat using a fast set of GPUs, it might be able to attempt 2 billion password combinations a second. If you algorithmically slow that process down, then it might only be able to take, say, 10 a second or 5 a second, depending on how many iterations you pass in. So you're making it much harder for people to crack those passwords. And to do this in .NET, it's incredibly simple. It's just that. So you've got a class here called RFC2898 derived bytes. Again, another bit of fantastic naming, but you just pass in a byte array of your password, a byte array of your salt, and a number of iterations. Then you say get bytes 20. The reason you say 20 is because it's using SHA-1 under the covers, not SHA-256, and that's a 20-byte hash code. So if we look at examples of numbers of iterations where I tested this at one point, so 100 iterations might take 2 milliseconds, 1,000 iterations might take 16, all the way up to 500,000 iterations, which might take 7 seconds. As you can see, the higher the number, you get linear growth in the amount of time. Now, if you're building that into your system, you need to work out what's an acceptable level of time for someone to wait. So I don't know if you've ever been on any websites where you type your password in, it feels like you're waiting about 2 or 3 seconds for it to log in. That's probably because it's doing something like this or bcrypt behind the scenes. But you need to work out what's an acceptable amount of delay for your users. So we're good, yeah? That's a good way of protecting passwords. But what we can do is go one little step further and add just a little bit extra to a password-based key derivation function using Key Vault, just to give us a bit of extra security. So this is what we've just looked at. But what we can do now is we can say that once we've hashed that password, we can then generate a hash message authentication code of that hashed password. Remember what I said earlier, a HMAC is just like a normal hash, but you have to pass in a key. And it's a 32-byte random number, just like what we did with AES. Now you can then go and protect that key using key vaults, using local key wrapping that we've just looked at. So effectively what we're doing is we're saying, we've got this hash password, but we're doing this extra hashing operation using a key which you have to recover with the key vault, and then we're storing the results of that hash in our database. So doing hashmacs is very straightforward. Again, this is how you do it in .NET. There's a class called HMAC SHA-256. You pass in a byte array of your key. Then you just call compute hash, passing in a byte array of what you want hashed, and it just returns the result. So what does this mean? So it means that if your password tables are stolen, and then you've got people using tools like Hashcat to try and recover your passwords, even though you've slowed them down using a password-based key derivation function, before they can even attempt to attack that hash, they've got to get through the hashmac that you've done first. But the only way they can do that is if they know the key that you pass into the HMAC, but that key is protected using Key Vault. So it just gives you that little extra sort of wrapper of protection around your passwords. This makes doing, dictionary and rainbow table attacks virtually impossible. Because for them to recover that key, they've got to access the Key Vault in a Microsoft data center. Microsoft are very good at building secure data centers. So one good practice for this is if you are doing this, you might want to have different hashmac keys for different roles in your businesses. So, we said we use the Key Vault to protect the hashmac key, and then that key to do a hashmac. But you might have different keys for different roles like admin users, internal employees and customers. You might decide you only want to give this extra level of protection to admin accounts. Might be something you want to do. So you only take that performance hit for admin passwords. That's up to you. Let's go and have a look at how to do that. Okay, so in this class, or in this project, I've got some sample code for building a hashmac, what we just looked at on the screen. And I've got the sample code for doing a password-based key derivation function. So let's use those together. Again, you can just download this and play with it and get a good feel of it yourself. So I'm going to create a new key on the Key Vault. This is a master key that I've created. I'm now going to generate a local key, just as we did before when we did the local key wrapping, and I'm going to encrypt that key. So that's exactly the same as what we did in the last demo. So I can go and store that key in our database because it's encrypted. So now let's come back. So we want to hash a password. So first of all, I'm going to decrypt that key. And then I'm going to have a string here with a really secure password. No one will ever guess that because I've put numbers in instead of letters. I generate my salt, so just like before, it's a 32-byte random number. So now what I'm going to do is I'm going to hash the password. So I'm using that password-based key derivation function, converting my password into a byte array, and providing the salt. In this case, I'm using 20,000 iterations. So now I have a hashed password as a byte array in there. Now that's where a lot of people normally stop. You convert that to a base 64 encoded string and you store it in your database, and that's your hashed password. So now what we're going to do is we're going to protect the password using the Key Vault. Well, using the key that's protected by the Key Vault. So what I'm going to do is I'm going to create a HMAC 256. I'm going to pass in the hashed password. So this is the password that's already gone through the key derivation function. And I'm going to pass in now the encrypted key, because we've already recovered the key using the Key Vault. So if I just quickly display those on the console. So the text a bit small on that one, so I apologise. But if you look at the top password that says hash password, that's the one that we've done with the password-based key derivation function. So you can see it's quite short, because it uses SHA-1 for that hashing process. But now I've gone and done a hash message authentication code of it using our key that we recovered via the Key Vault. And we've rehashed it, and that's now given us a much bigger hash. So we then go and store that in our database. So when the user logs in and we want to check the password, first of all we decrypt the local key, calculate the HMAC, and then we can also then go and calculate the password-based key derivation function. Okay. We're doing for time. Okay. Okay, so the last pattern to look at then is doing digital signatures and digital signing with the Key Vault. As we said before, so we've got 4 pillars of cryptography: confidentiality, integrity, authentication, and non-repudiation. So we've kind of covered the first 3, and non-repudiation is about creating digital signatures. So a digital signature is a mathematical technique used to validate the authenticity and integrity of a message, software, or digital document. Does anyone use services like DocuSign to sign contracts? But effectively what that's doing is it's generating digital signatures of that document. And there's 3 things you need to do that. So you need to be able to do key generation. We've already got that, because we've seen that already with the Key Vault. You need a signing algorithm, and you need a signature verifier algorithm. But the way this typically works is you, first of all, hash some data. So you might have a massive PDF of a document for buying a house, for example. You create a hash of that document, and then you use either a SHA-256 hash or a HMAC to hash that document. And then you create a digital signature of that hash. And the reason for that is because the digital signature under the covers is using RSA, and there's a limit on RSA in how much you can encrypt in one go. You can't encrypt more than the size of the key, which is one of the limitations of RSA. So that's why we create the hash first, and we sign the hash of the data. Now if we take a look at this, typically with RSA, when you encrypt data, you encrypt using the recipient's public key, and then you decrypt using their private key. Digital signature is the other way around. So in this case, Bob takes his private key, only he knows it. He creates a digital signature of the data, and then sends it over the internet, or the big spider's web, as I've drawn up there. Then Alice receives that digital signature, and then she uses Bob's public key to validate or verify the signature. If it comes back as true, she knows that that message definitely came from Bob, because only he has access to that private key. If the verifier comes back as false, then she doesn't trust it, because it can't have been Bob that sent that message. Now in .NET, when we do this manually without the Key Vault, there's 2 classes that we use. RSA PKCS1 signature formatter, and RSA PKCS1 signature deformatter. Again, brilliantly named classes, which is why a lot of people miss them in the framework. But we don't need to use those, we can use the Key Vault. So we've got no need to use those signature formatter classes. So let's go and have a look at that. Okay. So create my Key Vault, create a new key. So I've got a document here, or a piece of information I want to create a signature for. And it says this is a very important document. Could be a PDF document, could be a file, could be anything. So first of all, I'm going to create a hash of that data. So that's using just a standard SHA-256 hash in .NET. That gives me the hash in here. I've called it document digest, but it's just basically a hash of that document. Now I'm going to use the Key Vault. I'm going to pass in, I'm going to call the sign operation. I'm going to give it my key ID so it knows what key to use, and it's going to use the public key, the private key that's stored in the Key Vault, and I give it the hash of that document. So I've now got a byte array containing my signature, and you can store that, send it off to someone. Now I want to verify that a signature is valid. So again, I pass in the key ID, document digest, and the signature into the verify method. In this case, it's going to come back and it's going to say true. That's our happy path. So it's valid. We trust it. Let's run it again. So I've got my document, I create the hash, and I create the signature, just as we did before. I'm a dodgy hacker, I'm going to come in and I'm going to mess around with the original document. So I'm just going to go to that byte array, just change the first byte. So now what happens is when I pass in the document digest that I've just messed around with, and the signature into verify, it's going to come back and say false, because that digital signature doesn't match the document that we've passed in. But that verify operation was done on Azure Key Vault on the hardware. Okay, so in summary, we've talked about the fact that data breaches are getting worse. They happen all the time. But only 4% of those data breaches are classed as secure. So, reducing that top number is going to be very difficult. What we want to do is we want to increase that bottom number. So if it ever does happen to your company, you want to be in that 4%. Or we want to get that 4% higher, but you want to be classed as a secure data breach, so that your data is effectively worthless to anyone who steals it. So breaches are inevitable, you're never going to get around it. So it's not a case of if, but a case of when. I think it's a good mindset change to take. We've taken a look at Azure Key Vault. So we talked about the fact that traditionally hardware security modules have been very expensive, too prohibitive for many small companies. But Microsoft has very kindly produced a wrapper around a set of very expensive hardware that we can use, and using the techniques we've looked at, we can get that cost down to virtually nothing. And they've built theirs around the Phallus N-Shield hardware. I'm not quite sure how much this device costs. When I went to the website to have a look, it said, get in contact for details, which generally means expensive. Using the Key Vault is very simple. Setting up the Key Vault is very simple. The instructions on Microsoft's website are actually very good. And it gives you a lot of good explanation about how to set it up. But once we've done that, we talked about kind of 4 different patterns and sort of good practices that you can do around using a Key Vault. We looked at how with environments, you want to make sure you've got a separate hardware Key Vault for your production environment. Never share that Key Vault with any other system. We looked at how you can use the Key Vault to store secrets, so things like connection strings, application keys, and that sort of stuff. It's a good thing to do, store it on the Key Vault. We looked at local key wrapping, so you can get some performance improvements, so you're not hopping across the Key Vault every time to decrypt everything. You can just use local AES keys, which are protected by the Key Vault, but you can then do very fast encryption operations locally. We looked at how you can use key versioning if you want to. I mean, you don't have to use versioning if you don't want to. I mean, my examples didn't use versioning. But if you do need to use it, it's natively supported as part of the APIs. You can request specific versions of keys if needed. We looked at how you can use the Key Vault to add just a little bit of extra protection to securing passwords. And then we finally looked at how you can use the Key Vault for doing digital signatures, and how you can make that sort of process very easy using the Vault. All of the source code that we looked at is available there, so you can just take it and do what you want with it. It's released under MIT. It's been natively built for .NET Core, just because .NET Core is the new hot stuff and I wanted to use it on my Mac and not have to run up my Windows VM. If you are using .NET Framework, the code's fine, you just need to put it into a normal framework project. So if this is something you're interested in and you want some more references after this talk's finished, because your brains would have melted after the next 2 days, so if you want to go back and pick any of this stuff up, I've got 2 courses that might help. The play-by-play, which talks about Azure Key Vault and how to get it set up and how to use it, and then I've got my Practical Cryptography in .NET course, which goes into a sort of much more deeper dive about a lot of the crypto primitives in .NET and how to use them all together, because we've only really scratched the surface of what you can do with some of those primitives. Shameless plug, my latest course is called Blockchain Principles and Practices, so if any of you are curious as to how blockchains work and what they're all about, this course takes you through the theory, and it also gradually builds up a blockchain implementation in C# and .NET. So it's kind of like a computer science course. It teaches you the fundamental principles of how it works. Because what I found is a lot of companies, you sit in the boardroom and the directors are like, we need a blockchain. But they have absolutely no idea what one is. It's just a tool, and most of the time it's not suitable. So this course actually helps developers understand what they are and what they can be used for. And you actually go through the process of building one by hand. Also write a load of books that I publish on Amazon. The latest one is on social engineering, attack and prevention. It teaches you how to think like a criminal so that you can better protect yourself from a lot of their tricks. And that's it. Thank you very much. I'm going to be around for the next 2 days and at the party as well, so feel free to come over and say hi. And my Twitter address is down there. It's always good to have discussions in public on Twitter, as long as they're nice. Thank you.